Hi, my name is Paul Zhang, and today we are going to present our work on the importance of hyperparameter optimization in model-based reinforcement learning. We know that in general, RL is very sensitive to its hyperparameters. The same algorithm on the same task can have dramatically different performance with different hyperparameter configurations. This is particularly true for model-based RL algorithms due to their complexity and the fact that MBRL involves a non-stationary process where it needs to iteratively collect the data, train the model, and then plan. As a result, MBRL algorithms still requires time-consuming human expertise to be properly trained. To address this problem, in this paper, we performed the first study of HPO for MBRL, and in particular, we try to answer these three questions. First, how to find a good hyperparameter configurations without manually tuning it for a considerable amount of time. Second, how to demonstrate and address the non-stationarity of MBRL. And finally, what kind of insights do we get from tuning MBRL? So in order to answer these questions, we apply HPO techniques, including random search and hyperband. Additionally, we also use population-based training methods, PBT, and a variation of that, PBT-BT. PBT allows us to dynamically control the hyperparameter configurations and thus address the non-stationarity of MBRL. Let's first take a look at the non-stationarity part. For many RL tasks, the policy that we learn will change across the whole training. Therefore, in different stages of one task, we might need different hyperparameter configurations. For example, as is shown in the half-cheetah environment, we see that the half-cheetahs get involved over time, from standing to running, and finally it learns to spin. By using HPO methods, we managed to break the simulation in half-cheetah environment, and with dynamical training methods, we get even better performance. HPO methods also give us insights about hyperparameters. For example, HPO discovered that learning rate decays schedule without predefined scheduler. One important part which makes PBT work in MBRL is that it also copies the history when hyperparameters are changed. This indicates that MBRL is a non-stationary process. The hyperparameters and the corresponding training data are related to each other closely and cannot be considered or tuned separately. And these are the takeaway messages that we want to give you in our paper. HPO methods can automatically find good hyperparameter configurations and help you improve your MBRL algorithm's performance. Dynamical tuning methods can also help you since they address the non-stationarity of MBRL. Moreover, we show that when you are doing HPO on MBRL, do not forget your training data, which is highly tied to your hyperparameters. Finally, in the paper, we also further analyze the impact of HPO design decisions. Thank you for your attention, and I would like to invite you to take a look at our poster.